Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello, everybody. It's a pleasure to have Professor Bing Huang to come back. This is the second time. So a few months ago, when Zheng Yu from Collaboration and Communication Group invited him, he gave one talk somewhat as preliminary to this, but he's going to go over that again for the people who didn't attend that talk. So let me, I just talked to him a little bit about asking him to explain what extreme mean here. So there have been a little buzzwords around these days. And so I asked him whether extreme can be interpreted to be extremely simple. And he said, okay. So think about this one to be something really simple learning technique. But the beauty of simple is that you can use that as a little building block, like a Lego piece, to build some more fancy and more effective learning machine. So with this, rather than going through all his bio, I would just simply say that Professor Guan has done some really interesting work. And last time he gave this one version of this extremely simple machine, extremely simple learning machine. Today he actually promised to give something even simpler than the one he talked last time. So I'll give the floor to Professor Huang.
Okay, thank Nathan for the kind invitation and a very encouraging introduction. So actually, it's my pleasure to come here again. So last time, actually, I have met some friends. So this time, I saw see some new faces and also, I think some so-called pioneer, who I have been expecting for a long time. Yeah, so especially in neural network areas. Yeah, so today actually I also compare with the work done by the John Platt. Yeah, so last time I come here under the Zheng Yu Zhang's invitation. So during that talk, I just give a introduction to the batch external machine. So then we keep discussion with Li Deng. Li Deng has some very great ideas on deep learning, stack learning, etc. So then we say we found a major problem in learning is scalability. So today maybe I will focus on the scalability part. Okay, so basically today we will cover, because I found some of you haven't attended the first talk, so maybe the first part actually come from the first talk. So talk about.
Before you start, can you give us an official definition of extreme?
Okay, go back to the definition. This is actually there's a story behind. So we come out with this idea. This learning method first. So we don't know which name is good for this technique. So because those days we want to submit it to IEEE transaction on neural networks. So then I sit down watching TV. So then suddenly I saw a channel, Discovery Channel. So during that channel, there actually is one program called Extreme Machine. So in that extreme machine, talk about say sheep, so-called different kind of plane and a different kind of capacity. But so for the technique we developed, we found it's very difficult to just using one word to give the general ideas, cover all the ideas. It's not just a random. We also saw think of say whether we can use random something, but random too many kind of randoms. So it can't describe the main features of our method. So we say very simple. Yeah, it's very simple, but it may be very efficient. And sometimes we also consider the result also very good, testing accuracy. So then we say the channel extreme so-called program extreme machine. So then we say, why not? In mechanical, we have an extreme machine. Then why not in learning part, we have an extreme learning machine? But it's not replace other. It just shows something quite different from traditional learning method. So basically, it's kind of tuning free based learning technique. Okay, but it is very simple. It is extremely simple, extremely efficient, and I actually during the days we saw the result also looks extremely good. So then we say, why not extreme? So they actually borrow the ideas from the mechanical areas extreme immersion. Yeah. Okay. So we are talking about the feed-forward neural networks. So we are talking about general feed-forward networks and talk about function approximation classification. Then we also talk about SVM, because to me, I consider SVM is one of the solutions to generalize the feed-forward neural networks. Then we go to the learning theory we proposed. This part is different from the traditional learning theory. And then during this, because each theory will correspond to one algorithm. So based on this theory, we have one called incremental ELM algorithm. So this method is for us to build a network, called adding the node to the existing network one by one, node by node. But it actually looks very efficient. Later on, I show you. This one will compare with resource allocation network. This is a very, very popular, very, very famous one. And then we talk, because during this el-ELM, the network architecture looks big. So then we talk about enhanced incremental el-ELM, so we can get the more compact network. So this is very important for some kind of application which need actually is so-called maybe have a very large network data sets, and network architecture could be very large. So using this method, we reduce the network size. So then we talk about because last time we mentioned the el-ELM, but then many question is, is it similar to least square el-ELM, least square SVM, and also RBF network, right? So then we were mention the difference here, do some comparison. Okay, so then the last part we'll talk about online sequential el-ELM. So in this case, the data can be learned chunk by chunk, one by one, especially for those application which is very, very big. Okay, so you can't load all the data and train all the data in one time. So you have to, the better way to get the data, learn the data chunk by chunk, say 5,000. So next time maybe 6,000 coming, maybe 10,000 coming, right? So after learn the data, discard the data, okay? So now we go to the first part, because the first part actually we mentioned in the first talk. So just give a quick review. So there are two types of feed-forward networks. One is we call Sigmoid type network. So generally, the activation function is defined in this way. Okay, so then you have input layer, hidden layer, output layer. All right. So then the input to each hidden node is a weighted sum of the input from the hidden input layer. So, but for this, we can write this output of the network in this way, right? It's a weighted sum of the output of the hidden layer. So another major one is called RBF network. Okay, so RBF network in this case, right? So the hidden node here, output function, is a RBF function. So generally, most people are using a Gaussian function. But then if we write them, okay, so we can use the same formula for the output function, right? So we have weighted sum of the output hidden node, right? So in this way, we consider both sigmoid type network and RBF network is a kind of feed-forward network, right? So they have just single hidden layer. For both type of for this type of feed-forward networks, so people have proved this type of network have universal approximation property. So that means give any target function, okay, continuous function fx. So as long as the number of hidden nodes give here large enough, so the output of this network can be as close to your target function, right? As approximate to your target function as close as possible. I give any arrow, we can, in theory, we can reach that arrow, okay, that bound. So this is so traditional learning theory. But traditional learning theory has to tuning all the parameters here. So that means all the parameters in this single hidden layer feed-forward networks. So input the input width from the hidden input layer to the hidden layer, and the also hidden layer parameters, right? For sigmoid type is bias. For RBF network is the center, right, of the RBF node, and also output width here, right? So for this case, it's a beta I. Okay, so from a learning point of view, the target function usually is unknown. So then people have to do some samples, get the training data. So XIT, XJTJ. So we wish to ideally to let the so-called the output of the network, right, is as close to your target as possible, right? Okay, so then people have tuning all the parameters. So this is a traditional way. So single hidden layer can approximate any continuous target function. But how about classification? So previously we mentioned, so from classification point of view, we already proved, say, as long as this single hidden layer network can approximate any target continuous function, then we can prove this kind of network can differentiate any disjoint classification region. Means give any regions, no matter how many input dimensions. As long as this network can approximate any target continuous function, then this network can differentiate any, separate any disjoint classification regions. So that means as long as this can do universal approximation work, definitely in theory, this can also be used to do classification. Okay? Now, so from the learning method point of view, in the past, right, people using a BP to train the network, and all using RBF method to train the so-called this is square solution-based RBF solution, right, method for this kind of network. So usually two kind of BP or this square-based RBF solution. But based all this method, all the parameters have to be tuned. So now is another so-called very popular one is called support vector machine. So support vector machine is very, very popular. Now it's used almost everywhere, especially in classification. So, but of course, many people consider say SVM is not a kind of neural network solution. But if you read the Weblick 1995 paper, okay, so in their work, they consider, say, want to find a solution to multiple hidden layer feed-forward network. So then consider that instead of tuning the so-called inner hidden layers, just consider the last hidden layer. So last hidden layer, the output of the last hidden layer can be considered a fixture mapping phi xi. Okay, so with regard to the input xi. So the last hidden layer, the output of last hidden layer is phi x, right? So then they try to minimize, so let the so-called this kind of network to have this kind of optimization to minimize the margin, maximize the classification margin, and minimize the so-called training error, right? So then they get the solution for this kind of network. But generally, the output of actually the final decision function of SVM is this way. So you consider this, all right? But here, kernel actually can be considered a hidden node. All right. So here, alpha STS can be considered as the value of the output width, linking the hidden layer to the output layer. Of course, how to get the KXS, this is a kernel definition. Then they have to find the alpha STS, right? They have a different way to find it. Okay. So this SVM method, but generally can be considered as a solution, alternate solution to the multi-hidden layer feed-forward networks. Okay, the phi x is just the output function of the last hidden layer, right? Okay, so all this method, all the hidden parameter have been, can be tuned based on the conventional learning theory, means all the parameters have to be tuning. Okay, so then we found no matter SVM, RBF network, or sigmoid type network, right? So actually it's a kind of single hidden, can be considered a generalized single hidden layer feed-forward network. So you have a single hidden layer here. Suppose you have L hidden nodes. So then, so the L hidden nodes, this hidden layer actually can be considered the so-called the function of the objective of this hidden layer is kind of mapping. So we have a so-called the first hidden node, the output of the first hidden node is GA1B1X. The last hidden node is GALBLX, right? So this actually is a vector. This vector is output of the hidden layer. Can be considered vector mapping, right? So it can be sigmoid type network or RBF. So even other type of mapping function. So the idea is we mentioned before, say, suppose for this type of so-called single hidden layer feed-forward network, suppose there exists a tuning method. So you're tuning all the parameters, AI, BI, beta I, whatever. Suppose there exists such a tuning method for you to find the appropriate parameters, value for these parameters, right? So to reach your target, to solve the problem, okay? So then we say such a tuning is not required, okay? So in theory, that means give a target function, continuous target function f, okay? Give a continuous target function f. As long as the so-called the number of hidden nodes is large enough, then we can say all the hidden nodes, all the parameters AI, BI in the hidden layer can be randomly generated. And then you just need to calculate the output width, beta I. So as long as the number of hidden nodes are large enough, the output of the network can be as close to your target as possible, right? So actually with probability, it can reach 0, right? So this is a proof given here.
So do you have to prove any statement about the rate of that approximation?
Rate?
Yeah. How fast it is?
Oh, yeah, this is not. We ask several mathematicians. We say this is an open problem. So they try to do it, but it looks very difficult to handle. Especially, it's also related to probability, statistics, and also function-based, target-based. So it's a very good, interesting topic, but so far, very difficult to find a solution yet. Okay, so how to prove it? I just give a idea in principle. So our idea is, given a network, okay, suppose you already we added a node to the existing network one by one, because this is related to the largest data set application. So suppose you already have m-1 hidden node added to the network. So the current network has m-1 hidden node. So, of course, you have all the hidden nodes randomly generated. So whenever you add a new hidden node, you don't change the values of the existing parameters in the existing network. So that means for the existing m-1 hidden node, their parameter fixed. The output width related to this m-1 hidden node also fixed. what do you need to do? You need to random generate another hidden node, say GM, because GM is actually is a so-called output function of the M's generated hidden node. All right. So for this random generated hidden node, either this direction or that direction, it doesn't matter. So we just calculate the so-called optimum value for this the output width, linking this newly added hidden node to the output node. So the existing n-1 hidden node never change. Existing network never change. We just need to calculate the so-called value for the newly added network, the output of the newly added network beta m. How do you calculate it? Based on this formula? We just base how do we debate it? Because after you have added n-1 hidden nodes, your target f function is here, right? Target function is here. Okay, where's target function? Target, or this f, right? So the target is here. So from the target, actually there is a residential arrow between your between the target and the output function of the existing network with n-1 hidden nodes. So we just do projection. You get this value, beta m. So this is the projection. You get this value. So that is the optimum value for the output width of the newly added network. So then you are reaching here. So next time you add another one. It could be this direction or that direction, right? So either this direction. So again, you add another one, then get the projection, get the optimum value for the output width of the newly added network.
But next, what if that what's added is outside on opposite direction?
Yeah. So you say your direction is here, right? If that's here, then the beta value can be negative.
If you go to that direction,
Yeah, that direction.
you move away.
Now, if you add it to this direction, then the value of the beta can be negative. Then go here again, because your projection still come here, right? So it doesn't matter. So every time you add, then what happens? The residual arrow will become smaller and smaller. So we prove in this way. So we prove the residual arrow sequence, okay, will be convergent. So you find any subsequence of the arrow, you will definitely find a limit for that subsequence. So that means the residual arrow sequence is convergent. We prove this first. Second, we prove the norm of this so-called residual arrow is also convergent. So finally, we prove the norm of the limit of the convergence is 0. It's quite complicated, okay? But generally, it's based on kind of topology solution method. Okay, so basically, for this method, you see, it's very simple for you to add the hidden node to compute the parameter for the network. So every time you just add one, right? So that hidden node is random generated. So after you add one, you just need to calculate one parameter beta I for the newly added hidden node I. Okay, so you just calculate in this way. So this method, actually, this calculation usually is very fast. So from here we can generate a so-called a method, which for us to update the network. Okay, so every time, so you give a target. So maximum how many hidden nodes you can add, and then what is the expected error, right? So if you haven't reached your maximum number of hidden node, and the residual error is bigger than what you expect, so then we keep generate a new hidden node, add to the network, and then we calculate the value for the output width of the newly added hidden node. That's all, just the one. Every time, just do this. Okay. So then we compute the residual error for the newly built network. Yes.
It's not clear to me yet. How do you decide the first given the initial condition.
Just random generate. Even the first one, just random generate.
Then your proof requires that it's random.
Random.
But on the other hand, in practice, if you do something different than random, as I show you,
that
the
is
machine
not-
there, I just get much faster conversion. How do you explain that?
Oh yeah,
Yeah.
this is only for random generated. For your case is very difficult to prove. Yeah, but more interesting. My actually this proof. So after we give this proof, it looks very simple. But we spent 3 years or 4 years finding this proof. Yeah, so it's very complicated during the thinking with this way or that way. So finally we find a simple way to do it. Yeah. But I guess the proof to your case may be much more complicated because yours is not random generated. But of course, our case, when the first time you think about random, but how to prove it in random, it's complicated. But finally, it turns out that the solution is simple. But your case is everything is not random; it's deterministic. So the proof itself, I guess, could be complicated. Okay.
So,
Yeah.
So your proof is just about the convergence.
Yeah.
It doesn't say that
Conversion to zero.
zero. Yeah.
Yeah.
That doesn't mean your extreme learning machine is more efficient than the traditional one.
Yeah, not
So
efficient.
it's a different.
Yeah, different. Yeah, later on for the efficiency comparison we have to show based on simulation. Yeah. So for this case, you see, for different we test on of course 4 small cases because previously we don't have a large data set, we only have a small data set. So we based on the regression, you see they all convergence, right? So then this is average training time usually is just based on the depends on number of hidden nodes to be added. So it's a linear increase, right? So we compare, say, incremental ELM. Of course, here incremental definitely different from others. Okay. So later on we have another kind of so-called sequential method, right? So sometimes most people talk about sequential learning called incremental learning, but we have online sequential learning. So that means the data coming one by one or chunk by chunk. So we already defined that one as a sequential learning. So then for the architecture automatic updating, we call incremental part. So for this el-ELM, we apply sigmoid function, RBF function, and even sine function, cosine function. Okay. Then we try to add up to 200 hidden nodes. So then we test these several cases. We compare with another very actually pioneer one. Okay, it's similar. It's called work in this area. So resource allocation network proposed by John Platt, and also another one called minimum resource allocation. Okay, so with this the so-called testing accuracy comparison. So from here you can see usually the ELM generated better accuracy, right? So we also compare the, of course, standard deviation looks roughly in the same order or even better. You see the time, training time. You see the el-ELM uses training times here, say for this case 0.22 seconds. You look at the so-called resource allocation range, usually much longer. I tried this. I run all of them by myself. They have to tune numeric parameters. I guess 5 to 7 parameters to tune concurrently. Of course, after you tune, some of them can fix, but then still have 2 or 3 more have to be tuning based on application. So that means each of them you have to tuning parameters. For all cases, so far no parameters to tune. And then you see for this case, right, you have to spend quite a long time. Okay, but I use this, we don't know how to use remote desktop. So I have to run by a PC at home and run with the night have to come out to check the result. Okay, so this quite is fun.
el-ELM, did you increase it from 1 up to 200?
Yeah, we added the load from 1 to 200. This is the time.
You just use 200 all.
No, this is different.
That would be
Because
faster than this.
that is a batch learning we mentioned before. That is a fixed network. Yeah, it's a ELM.
Better than this? Incremental?
Network information usually is good, but then the time could be more time could be used. had to spend because
But I think incremental probably is a bit more efficient because you kind of check before you add a new one whether it's worthwhile to add or not. Right?
Yeah, but this one is more efficient because every time just calculate one time. That is very, very simple way.
But you need to calculate
200
by
times.
sweeping all the data, right? All the training data.
No, every time you see here, every time we just after we add one, we just remember the error. So next time we don't calculate the so-called recalculate the error for the for the existing network. We just remember error. So next time we just use.
Data once. I mean, don't question is you have to sweep data once every time you add one. Whereas if you have the batch, the batch in terms of the one shot, rather than incremental, you just do that once. You sweep that once, and then you can calculate this better.
Yeah, but the case is this is why I mentioned the scalability. If a data set, so your speech data set is very huge, it's very difficult to calculate the metrics. But I guess this could provide a possibility for your solution. Where every time we just add one hidden node, that means say even you have 200 million data, just 200 million calculation, 1 times 200 million. This is just one vector calculation. That's all.
But then it will be memory bound, so it will be very slow because every time you need to load data to the memory.
No there. Every time the data is after load, it just fixed there. Suppose the data is.
That only if your data can be fit into your memory, right?
Okay. The idea is after you load the data, what happens? You just need to remember the error. Right? So the data, of course, the data is still there.
You need to have data completely.
Hidden node.
You have to know that.
Yeah. Suppose the data already node. Of course, sometimes swapping there. That is, if the memory is limited, that is another case. Yeah. But suppose the data is already noded. I guess this would be very, very efficient.
But I think the value of doing this is that you can kind of automatically determine where you want to stop in growing your hidden node.
Yeah, you're right. So,
but in practice, I mean, we have tried some specific, the more the better. You never want to stop because error still, you want to keep dropping. Unless you have a simple problem, you might think that if error is 0.01,
okay.
Happy. And then
yeah. Okay, this actually raises a very interesting question I forgot to mention. Yeah, it's good. You see, of course, people can use cross-validation to determine where to stop. You see, for this case, it's very interesting. You see, the hidden node is randomly generated. And we only need to calculate the output weight for the newly added hidden node. So you see here, the decreasing very, very smoothly. It's different from others. Because we try this, you will run, so here is 200, 300, 500, one sort. It's always keep decreasing. Because for the single hidden layer feed-forward network, hidden layer play the major roles. But the hidden node here, randomly generated, it won't be determined based on training data or testing data. So if the hidden layer determined based on training data, the overfitting can be easily come up. But for this hidden layer, consider training and testing the same. You don't want to give benefit to anyone. So that usually is more, actually much better. It's much smoother. It won't so-called easily to get the overfitting. Yeah, yes.
So this way of doing incremental learning seems very much similar to the boosting, where you're adding one node by one, and then actually in boosting it's saying that you would actually prefer to use weak nodes, because the more weak, the less likely you will overfit.
Yeah, but here we want to consider that. Here we just give a basic idea. So actually, how to that could be a good point to say whether can be incorporated that ideas here could be. Yeah, but currently we haven't considered that. But
So
here we are using random. No, because here you see looks
you don't have a weight for each example in your training data.
Yeah. So here is a hidden node is random generated. I guess there is not, right? So then
Boosting, it doesn't limit how you decide what each node is. Basically, you can use random features as well.
Yeah. So, but here the actually original idea is we try to prove.
So the question is, are you able to make use of the boosting idea after you go through here, based upon the error, you assign different weights to the learning, to the data. That's boosting idea.
Yeah. So this is why we have yeah, that is so-called I say how to incorporate these ideas here or combine the ideas of the two works. I guess much better result could be obtained. Yeah.
So
but here you just give a basic idea.
To keep index on what samples make what kind of mistake.
Yeah.
And then based on that boosting idea, you can go back and what is data you don't deweight.
Yeah, that could be done later. Okay, so we also compare with this with a BP and the SVR, spot vector machine for regression. You see, we compare using the ELM with 500 hidden nodes, okay, 500 hidden nodes, compare with BP and the SVR. So you can see the accuracy here. Usually, IELM and the SVR can reach the similar result. But actually, the main advantage of IELM is here, you see, looks very, very fast, right? Actually, no parameter to tune, yes?
And how large is the input layer on these problems?
Oh, yeah, how large is, for this case, 500 hidden nodes.
The input layer, not the middle.
Input layer depends on the input dimensions of each case.
How large?
Oh, this is a simple case.
A few hundred.
A handful, maybe.
For input layer, that means the number of dimensions of each. For the I think this here is very, very simple, just the several tens or 20 maximum, because this is a very, very simple case for regression. Yeah.
One would expect that as that gets quite large, that far fewer of the randomly generated features will prove useful.
Oh yeah, your point. Yeah. Actually, last time later maybe I also mentioned the large score input dimensions. Yeah, later we have one.
So what is the hidden number in your BP?
Okay, so with the comparison here, so BP is this number of hidden nodes, right? So ELM is 500. Okay, so BP is here, and then SVR is number of vectors here.
So
Right.
if you use the same number of hidden units, will you get a better result than IELM?
Okay, this is another point. I will come back later. Here we fix 500. So later we have an enhanced one. This is just from our basic proof method. The proof method generates this kind of learning method. Okay. So even you compare here, even we have this 500, you compare with BP, it's still faster, right? So compare with a spot vector machine, it's much faster. But spot vector machine, you have to tune in these parameters, quite complicated, right? For IELM, no.
Oh, so this is only compared to time in terms of accuracy.
Accuracy is here.
It makes sense to have the same number of
Same,
hidden layers.
yeah.
The question: do you have the same number of hidden layers?
No, it's different because all number of hidden layers we keep adding until 500.
No, but when you compare with BP versus
No, you can't. BP is so-called tuning based.
No, but you fix the same number, right?
No,
use
can't.
the
You can't.
500 altogether.
You
Why
can't.
not? Why not?
We can't use, say, BP use 10 hidden node, then we say all methods using 10 node. Because you are random, even this direction, that direction, some is some is wasted, some is redundant. So it's input.
No, but you need to compare with the same architecture because in the decoding time, they actually cost the same.
You're right. So this is why we have to come back later. We have another one. So enhanced. Because these are very, very basic. This objective of this method is for us to prove the universal approximation of the batch of the fixed of the original extreme learning machine with fixed network architecture.
So I see the problem there. The problem is that random nodes actually are not efficient. You have to a lot, but it's unlikely to have overfitting because you don't train the lower layer.
Yeah, that's right.
Whereas if you use the same large number of hidden nodes for BP, you very quickly overfit. That's why you use
No. In this case, probably
you see, if you talk about BP,
in our case, we have 400 input. We have 2K hidden nodes. It's never overfit. So it's not a problem.
So maybe just training data maybe is very small.
No. I think he probably never tried using the same number of hidden units.
Okay, I'll come back later. You see later. Yeah, they will come back. This is an interesting question. Okay, So we also, you see, in a neural network, actually one challenging problem is to how to find the solution, learning method for a threshold network. So that means a single hidden layer feed-forward network with the so-called binary output function in the hidden layer. So actually so far no direct solution before that, right? Because binary, you can't using gradient method. For single hidden layer or multiple hidden layer, usually gradient method had to be used. So in this case, we're just using E-ELM directly. So that means E-ELM, the hidden node, just using binary function, okay? So then we compare this with BP. Because for BP, they try to change the gain factor, to make the gain factor large. So that means so-called the threshold network, threshold function can be approximated by the Sigmoid function with a large gain factor. Okay, so then we compare this threshold network trained by the E-ELM, actually I-E-LM. Okay, we added the hidden threshold node one by one and compare with BP. You see here, usually these are actually we get the direct solution. Actually, direct solution sometimes much better than this indirect solution. All right?
But you still use a different number of hidden units, right?
Yeah, different. Because
it's not a fair comparison.
So ideally, you need to tune that unit in such a way that you get the best performance. And I bet it will be more than 20.
Oh, that is different. We say a tuning free base, right? Okay. So now we go back to your question. So 500 large, really large, right? Compare is 10 or 50, which is used in the BP method. So then we say every time you just add one hidden node, add here, we just go further, right? So why not? Every time, in every learning step, we random generate several hidden nodes. We see which one so-called should be added to get the so-called largest decrease in residual error, right? So you add this direction. Okay, we say this direction better. Just go to this direction. So then after go to this direction, then next time add severals, right? Try to see which one generate several case. Okay, 10s or 20s. So which one to go, or this way or that way. So go that way. So this one actually the same method, right? Same method we can prove is universal approximation. Okay, so then the idea is same kind of algorithm, but then the interesting is conversion rate much faster. Okay, converge very quickly. You see,
it's only based on the number of hidden units, right? Not based on the total time. Because each time you need to calculate the several.
Later on I have the slide to show you to address your concern. Say for example, you see the sorted line, this and that. So the thin sorted line is the original. Here, I-ELM included one by one. Okay, every time just generate one. So the seeker sorted line is for the new one, enhanced one. So that means every time we generate 10. So among 10, we choose the best one. You see,
So
conversion rate quite different.
So you can do scale like 10 times in terms of time, but 10 times after you go through maybe 10 times more. Do they convert?
I will come back to this question later. So you see, I imagine this, okay, zoom in. So for this Abalone, I think this Abalone case, you see the original convergence curve is here. The new convergence is here. So in order to get the same accuracy, we say 0.09, these are target. The original one may be 330. So now, 21 hidden nodes. Get it? Yes?
So since the smaller set of hidden nodes is tuned to the data, are you subject to over-tuning them?
For this case?
Overfitting?
For this case, it's still the same, no. Because they're still using the same, because every time I just, get the same, so they still follow the same so-called, because or so-called series say, as long as you add one continuous, they always so-called one by one, then the residual error always so-called strictly decreasing. I mean, this is in theory. So the overfitting is not so obvious.
But did you verify that with cross-validation?
For this case, we don't. We just keep adding. You see, we just want to show the curve. Of course, until you add, definitely, I guess overfitting will come. What I fear for this case is not so.
You don't train a lot of parameters. This is the problem.
Yeah.
But
Because
all things are fixed, not random. You don't
But
train
here, we actually train it by selecting 1 from 10.
Oh, I see. So the only trend is by selection rather than.
Yeah. So overfitting compared to this, I guess if we can continue, it will come. So what I fear is not so obvious. Even if you see for this case, keep adding, it's still going. Yeah. It compared the earlier one because the earlier one just add. Right? It's no need to see which one is better. Right? Just keep adding. So for the first one, the overfitting is not so serious. The second one, although not so obvious, compare first one definitely is there. Yeah.
So this one actually addressed Don's earlier question that you get the 10 times of the computation to choose. Now it's roughly about 10 times.
No. You see, here we just using a 20 nodes. Here you have to use the 330 nodes. So which one faster? This one faster.
How many candidates per batch did you select?
Oh, for this is 10. I will come back here. Okay. So here we say you have a different number of candidates,
So,
right?
So basically, saying 21 versus 331, it is actually 210 versus 331, right? I mean, in a way.
Yeah. So if the time here is of course you add 21 nodes. Actually, you are already tried 221, 210 nodes.
How do you select the number of candidates?
Oh, yeah. So this here show the result. So if the k equal to 1, that means the original, basic, incremental. So if k equal to 5, this one, k equal to 10, k equal to 20. Of course, you go further, right? It will sometimes the curve will converge somewhere.
It looks like it will never converge, right? For the 1 versus 20.
Yeah, for this case, that means you will go 30 is still decreasing. Maybe for some case.
The one I told you, is Baltimore machine to do this. I bet much more sharper.
Yeah.
Actually, it will never converge. We try both. It just keeps going down all the way down.
For this case, I guess is a case also case dependent. Yeah. Any other question?
So there are basically 3 factors which are being traded off here, right? Accuracy, convergence time, and number of nodes added. I mean, so how do you decide the optimum thing? So this basically just shows the time which is required, right?
This is not the time. This testing.
What's the y-axis?
Yeah, this is testing accuracy. Root mean square error. Yeah. Of course, the original one is k equal to 1. This right. So usually we suggest because this case because actually it's run fast. It's easier for user to determine in your own case what is so-called what is the base number of candidates to be used, right? But generally we say we have a comparison here. So usually maybe 20 around actually is good for many cases. Of course, for specific case you may have a different number of candidates to be used, right? So we come back to the this data again. So we have the number of candidates k equal to 10 and 20. So we compare with the original one. So you can here, if you see the k equal to 20, you see the accuracy here. Actually, usually is here is right. Is better. Somewhere is, yeah. Here is better. This usually is increase. But of course, for this curve, I show is quite different because sometimes it's 0.1, 0.9, right? But if you show code, it's quite large. But if you show the value here, roughly in the same order. So this is, yeah, yes?
Also for most of your data sets, the accuracy values generally seem to be very low. I mean, did you try some different data sets where accuracy values are relatively higher? So, I mean, for most of our data sets like SVM supply accuracy of more than 60-70%. While here, I don't even see more than 20% anywhere.
So this is a regression?
This is for regression.
Oh, yeah.
This is for regression.
Okay.
Yeah. So this, okay. So this compared to.
But I have one comment. So basically, when you select the 1 from the 10, you are using only the zeros or the information, just the value of the function, right? If you use the first order information like gradient or something like that, you will get
faster convergence and better network. Actually, we have some work done, I think, and that we can show that it performs much faster than this one.
You're right. So here is a very basic basic idea. So first great so-called how to get the so other information to be incorporated into this method actually can be another very interesting work. But so far we just go to the basic. So whatever result we're showing here is just very basic result.
I think you compare only the training time. That's probably not very important training time.
Mm-hmm.
The important thing is here you have much smaller number of.
This is a case and read.
Yeah, I understand. Yeah. I said the network you trained with this multiple selection is much smaller than the original one. So the test time is much faster.
Right, but if you use a first order information,
you will have even smaller,
even better. Smaller.
Yeah, that would be that could be. And here because you're using here because you get a smaller network compared to the earlier one. So this is okay. This is a testing standard deviation. Okay, so you compare the so-called. Okay, so this a lot. Oh yeah. Okay, so then that is so-called how to add the hidden node one by one. Because we haven't tried the large data set because currently we just interested in proposing algorithm, right? So I think it has a lot of large scale, large data size of data. I guess that could be tried because every time just add one, see what's the performance. So that is so-called add the hidden node one by one. So then so what is the relationship between the so-called that work and the work and the extreme learning machine with a fixed network architecture? This we mentioned in the first talk, right? So that proof that incremental algorithm tell us. So the network architecture for this kind of network architecture, the hidden layer need not be tuning, can be random generated. So since random generated, we mentioned last time, so then the training of this network become very simple, right? So given the training data xj and tj, we wish to have the output of the network, right, equal to your target. I mean, this is ideal case, right? But usually, so in this case, given the n training data, so we have the n functions, right? So L means number of hidden nodes, means L unknown parameters, right? So in this case, we can write them in a so-called matrix format, right? So then we can have h beta equal to t. This we mentioned before. So in order to get this h beta, solve this problem, we just need to get the value to solve this this equation, right? To get the beta. So we just random generate a hidden node and calculate the hidden layer output matrix, and then do pseudo inverse get the beta, right? This is the basic idea. But we mentioned before, so from the region regression theory point of view, right? In order to get the stable solution, in order to get a stable solution, so in the calculator pseudo inverse, we better to introduce the so-called regularizing parameter, so added in the diagonal entry part. So add I over C here, okay? So for left pseudo inverse and right pseudo inverse. So after you get this, then what happens? So basically for ELM, if the network architecture is fixed, all right? Because network architecture fixed, previously we added the hidden node one by one. But after network architecture fixed, so what is the best solution? Use the square method, right? So we just use this square method, then get this solution, right? So H here is random generated. For this case, we just add the recognition factors there.
So in practice, most of the time use the first one, right? Because it depends on the rank of the matrix.
It depends on your application. Because so your target or target is different. We want to say
We have these two solutions, right? Depending
Yeah.
on it's a fat matrix or
Yeah, that's right. So your case is your data is very large.
It's the top.
So then you have to use, I say, the first one, right? Oh, yours is the second one. Yeah, yours is the second one because here is n times n h is n times l, right? So yours is second one because finally become l times l. The size of the matrix is l times l, right? So then we say, if h is unknown, if the hidden layer output function is unknown to us, so then we say we can using the kernel define a kernel method, right? Okay, so then we define a kernel method. These are kernel. So that means hxi times hxj become kxi kxj. Okay, so now what's the difference between this and this square method, right? So this is one of the main topics here because many people are interested in this, right? So okay, so for long kernel method we have this. Actually, from this first formula, we can get this. Suppose hxi times hxj equal to kxi xj, right? So this is a kernel definition, right? Using SVM and other kerning method. So this method, you see the same formula for regression, for binary class, for multiple class. So how about this square SVM? This square SVM here, all right? This square SVM. For binary case, they have this formula. Okay, for proximal SVM, they have this formula. Right, so compare this. This looks much simpler, right, in terms of implementation. And then from here, you see they also have, for this square SVM and the proximal SVM, they also have the kernel score matrix, Z times Z transpose, right? So Z is T1 phi x1, Tn phi xn.
So why you say it's simpler? I mean, that is only two elements, right? This is very large.
No, they have to solve the same matrix.
Oh, the same. Oh,
yeah, so here also matrix is n times n. So here also n times n, right?
So it should be the same, huh?
Yeah, but you see the formula here is this looks more what I say?
Unified.
Yeah, unified because it's all consistent. And this for binary. And then you see there for this kernel matrix, their definition kernel matrix depends on the output target also T1 to Tn. But for this, actually is irrelevant to the so the kernel matrix is irrelevant to the output target, right? Okay, so these are three different.
No, but in terms of computation, I mean, SMO fast method to do this.
No, SMO not used here. SMO usually using SVM. Okay, so this for this square. I just compare with this SVM. So why? So for multiple class, for this square SVM, multiple class is here. So that means you have the so-called so-called M classes. So then you can use M this square SVM, right? So it's for one class, and then they have this. But for ELM, we just have one. Okay. So yes.
You write this right hand side, it should be the same. Basically, we taught this. If you rewrite it into a matrix form, then it will be the same.
No, it's different. Actually, yesterday I saw it different because here omega m and here there is quite. You see, there would be n times n then. Because you have that matrix of n times m matrix.
But at the end, you still solve linear system equation, right?
Yeah.
So the solution is it just doing the inverse? So the main computation eventually come down to the inverse.
Yeah.
With a very large matrix.
Yeah. Finally, still we just solve this one. You see, from here, if you talk that say they are similar, actually even here and here also similar, right? So
the question is what in terms of the size of the matrix, you need to do the inverse. Which one is larger? This one is just huge, right? We talk about
if we talk this one, the so-called for binary case, I think the complexity that's the same, right? Because they're all both in the n times n. If we talk about multi-class, what happens? There will be nm because they were if we put together, right? It's they for each class they have to do so-called n times n, right?
You do that n by n matrix inversion n times. Is that right? I think you do that n times rather than
here you only have a 0 or 1, so you only have one target.
No, here you have m. Here, suppose you have m class. Each class is n times n, right? So m class, because here you have to compute m classes, m classifier. So the total time is m times n squared, all right? So here, just 1, right?
Here is the same because you have some matrix form. So the total.
No, the matrix size here is n times n. These are fixed.
This inversion part, I think, is the same.
Yeah.
Because the only difference would be how you times.
Even here is just n. This fixed.
that part is easy.
Yeah, it is fixed. So it's always here is always n times n. Here is n times n squared, right? Okay. So why you see here and here the formula different, right? So why this square SVM and the PS-SVM are different final solution? So actually the key point here, they so-called, you see this square SVM and the PS-SVM, so they have the same so-called constraint, but the target function is different. For approximator SVM, they just add a bias here, right? So then they generate a different solution. And then for how about El-ELM? The target function same as this square SVM, but the condition is different. You see the condition of the El-ELM is different from the rest 2. For the El-ELM, we don't have the B here, but that is a bias of the output node. For the least square SVM and PS-SVM, they have the bias in the output node. Because what's the reason? Because El-ELM is come from the universal approximation first. We say the hidden node have to satisfy universal approximation condition. So that means ideally H beta equal to T, right? This is our target, H beta equal to T. So we do not need to have a B there. But for this square SVM and PS-SVM, they come from SVM. Because SVM previously come from classification. So when we talk about classification, in the first place, they didn't mention the universal approximation. So ideally, should have a bias in the output, right? Because you either hyperplane here, and that could be possible, although parallel to each other, right? But their so-called hyperplane may not pass through the origin in the fixed space. But the El-ELM has to satisfy universal approximation first. So ideally, in the fixed space, that means that so-called hidden layer fixture mapping space, so the separate margin should pass through the origin. So we do not need to have B here. So this is the main issue. So due to this B, the problem comes. If you see this square SVM and you see that is the primer so-called optimization problem. If you see their dual problem, if you see from a dual problem, you can see because we all have to satisfy KKT condition. So this the square SVM, if you check the KKT condition, due to the B issue, they have to satisfy this. This is a square solution. They have to satisfy this condition. So what is the condition? That means their parameters have to obtain from a hyperplane here. But for El-ELM, no constraint, no such constraints there. So that means El-ELM have to get a solution in the entire space. No constraints.
No. So all I'm saying that if you can modify the support SVM formulation originally, saying that you can strain your hyperplane to pass through origin, you'll be identical.
That's
that's
right.
not optimal in terms of SVM formulation in terms of minimizing margin.
But
So
SVM say linear, polynomial, or the kernel can be used. I mean that is true because different application may have actually so-called different kernel may be better for different applications, right? So that is true. So even linear used, but linear in our case can't be used because linear you can't say universal approximation, right? So if you say add that condition there, then SVM become here. But then you can't use a linear. Then that means SVM built a very big house, very perfect, beautiful house. can be used here or there. That's true. Without the SVM, last time I mentioned, the world will be different. Definitely, even your speech recognition, face recognition, quite different. But the issue is, I say it's too good because it's too perfect. So it covers too many things. So we have to make it a thing, right? So that means, okay, you have this. Okay, I just use the universal part. That means the kernel have to satisfy universal approximation. And then this square SVM, right, is here, also follow the SVM. We say, okay, we just universal approximation part. Then everything becomes simplified. So then finally we get this, right? So then the solution becomes very, very simplified, simple. So this is the target. Of course, if we say generate all the similar, but then after remove those redundancy, unnecessary condition, and finally you say, then finally everything becomes unified. So in this case, we don't have the one against one problem, one against all problem, right? So everything becomes similar. So if we talk about SVM, you have to talk about supervised machine regression. Then for this case, same formula for all. Okay? So this is one part I want to.
Can you go back to the previous slide? So, from what I understand, the reason you want to have this constraint is exactly the benefit of SVM, which gives you better generalization rate. Because you constrain your weight space, so you can get better generalization.
No, for this case is no. For this case is because this kind of plane is not come from the so-called the maximum margin, the minimum norm. It come from B, because the buyer B there. So in order to say in order to solve the so-called optimization problem, right? You have to do some kind of gradient with regards to B. In that case, condition on B will generate this condition. Without the B, this condition will be no more there. Okay, so this similar to SVM issue, the same. I don't call it a kind of actually it's because this comes from the original because classification issue and so on, right? Okay. So generally, ELM say hidden node need not be tuning. Then the hidden layer should certify universal approximation. Then we have to certify these two targets. Okay. Right. So this.
No, talking about universal convergence condition. When you use this kernel method at the end, how does that proof carry over? It probably doesn't.
It also.
Does this work? Well, you don't have the concept of the hidden nodes here, right?
No.
The whole thing is combined.
Because we say so. This is why I say we do not. ELM does not work for all the kernels. We have to say the kernel have to satisfy universal approximation. If the kernel satisfy universal approximation, then it works.
So how do you judge whether?
So this is another issue. Because now you say this kernel work, that kernel work, but we say no. For all cases, maybe better to have the kernel certify universal approximation. Because if you do not certify universal approximation, means some application there, so some target function, you can't match, right? So that means it can't be used everywhere. Of course, it can be used here, good, but it may not be used other place, right? So this okay.
The question is, suppose I give you a fixed kernel, like a Gaussian kernel. Then how do you know whether it's certified?
No, that is proved. That is already proved in theory, yeah.
But not in terms of the earlier proof again.
Different.
It's a separate proof.
Yeah. So we tested. So actually we added here is the mean list, right? It's 60,000 training data and testing data is 10,000. Input dimension is 28 times 28, so it's 10 classes. Okay, so because the rest we already mentioned before, we just highlight here. So for mean list, so we refer to the Hinton science paper. So he mentioned SVM can reach 98.6 testing accuracy. Then his deep learning method is reached 98.8 accuracy for the training data, all the training data, 60,000 training data. So we test ELM method. We run ELM in mean list, we get the accuracy 98.7 with 50,000 training data. Of course, because we use more memory. So then due to the memory issue, we can't run until can't use all the 60,000 data. We just use the 50,000 training data for this case, but reach here. But if we add another 10,000 data, I guess maybe reach the 98.8. Okay, of course, Nideng has a lot of powerful kind of tools. So stack learning, deep learning further. So I guess you combine with his work, maybe I think can be higher than 90%, right? This is our expectation. Okay. So that is so far we talk about the add a hidden node one by one, right? So this actually I see could be used efficient for the application with large data set. So another case is say suppose the data so-called the network architecture is fixed. So can we learn the data chunk by chunk? So in this case, the data can come in one by one or chunk by chunk, right? So at any time, only the newly arrived data can be learned. So after you learn the data should be discarded because you don't know how many data will come. As long as new data come in, you have to retraining all the old data, then that would be very, very time consuming. So in this case, whenever a new data come in, you just learn the new data. After the new data has been learned and discarded, okay? So then the next is, suppose the method does not have the knowledge on the application and so on. So in this case, how do we train the network? So we can use an el-ELM because due to that simple formula, I have to say due to that simple formula, right? So then we can use the recursive, based on the recursive square method. That is a simple matrix method. So suppose you have a large matrix, right? You want to do pseudo inverse and so on. So how about we get the first several rows first, and then add the next several rows, and then the next several rows. So finally get a solution on the entire inverse of the entire matrix, right? So this is the method for us to solve the so-called application with larger data. Okay, so we compare with the several. Of course, here is a simple or the small data set here, right? We use a Sigmoid hidden node, RBF hidden node, or compare with stochastic, BP, and some other algorithm which can learn the data chunk by chunk or one by one. Okay, so this is the training time, right? So this is the testing accuracy comparison. Usually it's fast, good.
So again, for stochastic BP, you use the smaller number of hidden layer. Oh, it's small. Oh, this is
here.
identical.
Yeah, so 13.
It's smaller.
Yeah, 13.
Yeah. If you use 25, do you get better result?
No, overfitting.
Overfitting.
Yeah, so this we have tried to get the best. Yeah, because for BP based gradient, okay, each node had to tune in very carefully, so exactly. So remove one, add one will be quite different. But all is because random generated, so here add one, there one, so really very flat. But of course, too few it can't work. Too many, not good, right?
So sorry, so what is the size of the training set?
No, this size is very, very small.
Very small.
Yeah, this because we just want to see whether it's work. Okay. Yeah. So also we tested in the Mackie class case. So here we also can data coming chunk by chunk. So this bracket means the data can be randomly generated. The size of the data is randomly generated between 10 and 30. Sometimes 10, 15, 20, or 30. It's not just coming one by one. Because most of the existing so-called online sequential learning methods just learn the data one by one, okay, instead of chunk by chunk, right? So here is a DNA case, right? DNA case is high input dimension. So this is the accuracy we can achieve. This is the original one without adding recognition factor. After you adding the recognition factor, last time I mentioned, the accuracy is very, very high. Okay, same as SVM, right? Okay, so this come to the conclusion. The most of them I already mentioned before. So then the issue is for the kernel method. Because kernel method, right, we test is for mean list. Actual accuracy is 98.7, is almost the same as the rest. But then for the large data set, right, large memory will be required. Usually auto memory, say you have several million of data. So how do we handle this? Because several million of data, you have the metric will be several million times several million. So it's very impossible for us to handle. So then the key points is, can online sequential learning be implemented? Right? We all students have done something along this direction, but I guess this direction is open, is still open. It's very, very challenging, especially for SVM. SVM, right? People try to have the incremental or online sequential method, but so far, very difficult, still very difficult to handle large data set, right? So can we do it? And then the second is, can we prove so-called, actually it's not always, it usually provides better general performance because the hidden node is random generated, so sometimes it won't give the bias to the training data or testing data. So usually we found if the same kernel used, say same Gaussian kernel used, in the simulation done by us, actually also done by others, researchers, ELM usually get a better better general performance than SVM and this square SVM. And the reason actually I just mentioned. Of course, that is the reason I mentioned. Can we rigorously prove? That is just a kind of intuitively speaking. Okay, so then ELM, whether ELM is always faster than this square SVM. All right, so this could be, I think can be also proved because you see from here you can see it. Because ELM solves this formula. SVM, and this square SVM solves this formula, right? So it's, at least we don't have this part, we only have this part, so, right? So it's, for the binary case, similar, right? But if you have multiple class or whatever, this looks similar. At least this won't be slower than this square SVM, right? So this is a conclusion. Okay, yeah, thanks.
So can you go over this proof for the kernel case with the convergence? So the earlier proof you gave actually assume that you add one hidden unit at a time, and then you can show that error, reduced to 0. Right?
Yeah.
Now for the kernel case, how do you do that?
No, for the kernel case, the network architecture is fixed. So the Gaussian function, they suppose Gaussian function. Not all the kernel, for the Gaussian kernel, that is already proved before. That is just, it's not come from my proof.
So, I see.
Yeah,
Okay.
my proof is for random. Yeah, and then we say this method can be extended to kernel method because we say just one step away. So then we extend from random to the kernel machine, right? But not all the kernels. It's just some kernel which satisfy universal approximation condition. Yeah.
Okay, that's good. So any more questions here? Okay, great. Thank you very much.
Thank you.